All right, so welcome everybody. So I'm going to start with the good news that your lab reports went, I think, really well. Some of you guys just did some outstanding jobs, outstanding. Some of you, very few of you guys didn't make a connection, and I gave you an opportunity to redo your circuits. You can actually make a connection so that there'd be actual current flowing. Anyway, and I was pleased to hear comments. Everybody found it pretty easy to use that. The second thing was you guys did pretty well on the chapter 18 test. So the average was a 71, so that was pretty good. So yay, congrats. The big thing I want you guys to know is for conceptual physics class, instead of a final exam, there's going to be a research project. So you guys get to write a paper. Now this paper, I hope I didn't get it ready. This paper, I already posted the rubric. And in the rubric, I want to be really, really clear that there's 3 things that you guys have to explain. And I didn't pull it up here. I've got to go find it. You guys got to explain. And we're going to be learning that together today and next week. So I want to make sure you understand how to do it and what it means so that you include it in your paper. Because basically your paper is, how does a motor work? Why does a motor work? Shoot, you guys, I'm going to go ahead and see if I can find that rubric so I can show it to you guys. All right, let me see here. Sorry. Is it here? It is, yay. Okay, so I already posted this online, and so, oh, this is not the right one. So this is not the right one. So I'll have to look for it later. This is, it's the same information, but I actually gave you guys even more detailed information of what I want in that research rubric. Anyway, so we'll talk about later if I've got some time at the end of the class. All right, so since the physics final, science finals for seniors is on Monday, June 8th, that is when your paper's due, but it's due at 8 a.m. So you might as well finish it Sunday night, okay? Might as well get it done because I will not be accepting late assignments. And I'm gonna be real hard-nosed about that just because that's how it's like in college. If you don't turn it in on time, it's not gonna be accepted. Let me let Helen in. All right, so again, your final exam instead is going to be a research project. Make sure you guys see that. All right. So paper on your how does a motor work, and we're going to be talking about electromagnetic force, electromagnetic magnetic fields, and we're going to talk more examples specifically. So the stuff that we're going to be learning about the next couple of class meetings is the basics of a motor. Okay. All right. So let's see. Next thing. I think most of you guys saw the video that I made for you guys, Styer video number 1. And I actually show examples of a hang crank motor. And actually that's a generator because you convert mechanical energy. That's when you're turning your hand, turning the crank with your hand. And then that mechanical energy gets converted to electrical energy. So interestingly enough, a motor is just the opposite of a generator. A generator converts mechanical energy into electrical energy. And the motor does it the other way around. It takes electrical energy and converts it to mechanical energy. So like the motor in your car is, you're going to be using the battery, getting electrical energy, and then transfer that and convert to mechanical energy to turn the wheels of the axle. All right, so in that video I showed magnets, the magnets that you guys would have played around with in the classroom. And so I want to make sure you guys know that. The other thing is I want to make sure you guys have the 3 handouts. I posted the handouts. The handouts are of chapter 19, magnetism, and electromagnetism, the motor effect, and electromagnetic induction. There's something called a right-hand rule, which we'll go over with today. And then there's going to be the left-hand rule. And the left-hand rule you really want to understand because that's what really makes something turn. So such as in a motor. All right, so we're going to go through a couple of short videos, and then we're going to talk about a solenoid. What is a solenoid? That's pretty important in a motor, and you'll understand why a solenoid is important. All right, so we'll start with the magnet and the poles of the magnet. Let me go over there to that video. and I believe I need to do a share screen. I'm not sure if you guys can see that. So yep, it looks you can. All right, so we're gonna start with this video here of the magnets. Here we go.
The parts of a magnet where the magnetic effects are strongest are called poles. Magnets have a pair of poles, a north pole and a south pole. A magnet's north pole always points north and its south pole always points south. Poles that are alike repel each other. For example, two north poles repel one another. Likewise, two south poles repel one another. However, two unlike poles, north and south, attract one another.
Okay, pretty straightforward. Hopefully you guys have had a chance to play with magnets in your life. All right, here we go with the compass. Here's the compass. Why is it that the compass will always point towards the North Pole, the geographic North Pole?
The north pole of a compass needle points in the direction of a magnetic field. To show directions of magnetic fields in drawings and photographs, we use a set of three symbols. A series of arrows shows the direction of a magnetic field in the plane of the paper. A series of dots for the heads of the arrows represent a magnetic field pointing up from the page. A series of X's for the tails of the arrows represent a magnetic field pointing down through the page.
Okay, pretty straightforward. That's just how you can show that on paper. All right, so the next thing I want to do is show this video if I can find where I did with it. Here it is. Okay, here we go. Hopefully you guys can see this. Uh-oh. There we go. Play again.
Produces a magnetic field. Here we see iron current flowing.
Let me start from the beginning.
Produces a wire that has current flowing through it. Produces a magnetic field. Here we see iron filings forming a pattern due to the magnetic field created by the electric current. The direction of the magnetic field is determined by the direction of the current in the wire, according to the right-hand rule. If the thumb of your right hand points in the direction that positive current is flowing, then the magnetic field goes around the wire as shown by the curling of your fingers. In this example, the current is flowing upwards, so the magnetic field points in a counterclockwise direction. The symbol B refers to magnetic field, and the symbol I refers to electrical current. A wire that has current.
Okay, so I'm going to explain this again. It's a little fuzzy because I made it bigger. But bottom line is there's something called metal filings. It's like taking metal and you've got sandpaper and you can sand it and get little tiny little pieces of metal. So they're metal and it's magnetic. So that's what these are, metal filings. And this vertical line represents a wire and we have current going through it. And it turns out that if you have electrical current going through a wire, you will create a magnetic field. Similar to a magnetic field around a magnet, except there isn't a magnet, it's just a wire and electricity. And the way we can show which way it's going is the right-hand rule. So I'll stop when we get to the right-hand rule. Listen to this. What you want to notice is which direction of those filings kind of going around in that circle.
Flowing through it produces a magnetic field. Here we see iron filings forming a pattern due to the magnetic field created by the electric current. The direction of the magnetic field is determined by the direction of the current in the wire.
All right, so I want to explain this part here. This only works with your right hand. So if you show your right hand like the way it is in the picture and your thumb is going straight up, the thumb is in the direction of the current. So that means that the current is going from the bottom of the page here up towards the top. So if it's going from the bottom to top, in the direction that your thumb is pointing, and then you close your fingers around, the way the fingers are closed around is the direction of the magnetic field. So if you put that hand really close to your chest and your nose is looking down at your thumb, you'll notice that your fingers are going in a counterclockwise direction. So that's the deal. You have a counterclockwise direction of magnetic field that was pushing those metal filings in that direction because the current is going up. If you were to change the direction of the current, you flip your hand down, and now if your thumb is down pointing towards the floor, you'll notice that your fingers that are curled are going in a clockwise direction. Okay, let me let her finish up.
According to the right-hand rule, if the thumb of your right hand points in the direction that positive current is flowing, Then the magnetic field goes around the wire as shown by the curling of your fingers. In this example, the current is flowing upwards, so the magnetic field points in a counterclockwise direction. The symbol B refers to magnetic field, and the symbol I refers to electrical current.
All right, so now what I want you guys to see, hopefully you guys can still see the screen here. They took a wire, instead of it being straight, they bent it one loop. Notice it just, the current is going out, then it's bent into a loop, then it comes back. Well, if that's the case, you still are going to have a magnetic field, except the shape is going to be depending on which direction the current is. So listen to what she says.
A common way to create a magnetic field is to create a current in a loop of wire. Remember the right-hand rule for magnetic fields created by currents. If your right hand is here, with the thumb pointing in the direction of current flow, then the curl of your fingers shows the direction that the magnetic field points. The field wraps around the wire, as we have seen before. Now let's investigate the magnetic fields created by this part of the current loop. Again, point your thumb in the direction of current. The curl of your fingers will show the magnetic field that wraps around the wire at that point. Notice that the magnetic field formed around the other part of the wire was similar. Both magnetic fields point upwards inside the loop and downwards outside the wire loop.
I wish they had drawn more of these little blue circles, because this isn't just happening on the right and the left, it's happening all the way around that loop.
The current in every part of the loop helps create an upwards magnetic field in the center. Outside the loop of current, the field points down.
So what happened here? You've created a magnetic field that looks like one that a magnet creates, except it's not a magnet. But you've created the same kind of magnetic field as a magnet did.
Notice that this is very similar to the magnetic field of a bar magnet.
Okay, so that's the big deal. All right, so what I want to do is show an example of why you care about this. So there's two different things I want to show. First of all, I want you guys to know what a solenoid is. In this example here, there's only one loop. But what if I did a whole bunch of loops? So the wire goes in and I go a whole bunch of loops and then the wire comes back out. And that would be an example of a solenoid. So I'm going to switch over to a PowerPoint. Here we go. And I got to make sure I can share that screen. Oh, you guys still see that? All right. So here we go. This is an example of a solenoid. Instead of just one loop around, you'll notice that there's the current is coming in from the bottom, going up, and it goes around this loop, around this loop, around this loop, around this loop. This is all this copper wire, let's say. And at the very end, it goes out the other way. So interestingly enough, because of the right-hand rule, because you've got current going through a wire, you have created a magnetic field. And this magnetic field pattern that you see looks just like an actual bar magnet, like a regular magnet. Now, why would we care? Well, we know that if there's a magnetic field and current, well, now we can just create current for a purpose, like a motor. And we'd rather use this instead of a magnet because the magnet doesn't turn off. The magnet always has that magnetic field around it, always, always, always. But here I can turn off the current. And then I can have it on or off whenever I want it to be on or off. All right, so let me see. I have one more video to show you guys, and then I want to show you this short thing about what is a solenoid. All right, let's show that other video. I've got to switch back over here to this one. Oh, I guess that was it. That was it. I didn't show you. I didn't have it ready. Sorry about that. Thought I had it ready. Okay, please hold. I have to get it. 18. Here we go. Oh, I already showed that one. Okay, sorry you guys. Okay, so what I want to show you guys is the one about what is a solenoid. So let me see if I can get this link here. It's only about 2.5 minutes. And I got to make sure you guys can see this. Hold on, before I start it, I want to make sure you guys can see this. Share a screen. Okay, here we go. All right, so now we're gonna go inside a big old, a small one, but we're zooming in a solenoid. Here we go.
Take a long coil with many circular turns of insulated copper, wrapped closely in the shape of a cylinder. This type of coil is called as a solenoid. The electromagnetic effect of a solenoid is used in several appliances. Let us pass electric current through the solenoid and observe the pattern of magnetic field lines demonstrated here. The magnetic field lines in a solenoid are same as in a bar magnet. They pass through the solenoid and return from the other end. The field lines inside the solenoid are parallel to each other. The parallel lines will have the same magnitude of the magnetic field. That is why the solenoid has a uniform magnetic field. If we suspend this current-carrying solenoid freely, it rests pointing north and south, just like the suspended magnetic bar does. It shows that on passing electric current, the solenoid turns to a magnet having north and south poles. When we take a piece of soft iron inside this coil, the iron piece is pulled inside. The electromagnetic effect performs the mechanical function of pulling. The system of a coil with soft iron core is used for several electromechanical applications, such as start or stop actions for valves of the dishwashers, starters of vehicles, pull and push agents of the door locks, etc. The current-carrying solenoid converts the soft iron into an electromagnet. When the current is stopped, the solenoid is demagnetized. Even the soft iron core also loses its magnetism.
All right, so
Take
let me
a
stop.
long
Oops.
solenoid are parallel to each other.
Shoot. Okay, so the next thing I want to show you guys is an actual example. So hopefully you guys can see this is an example of a solenoid. If you can, I hope I zoomed in, you can see, although there's a little piece of plastic covering it, copper wire wrapped around really tight around this circle, this little cylinder. And on the side, it says how many. There's 400. Later on, when we get to step-up transformers, step-down transformers, you'll know why I need to know how many loops there are here. But anyway, this is a solenoid. Now, in the other example I showed you guys in that first video was of this hand crank. I know it's kind of tough because this too close to it. But this is that hand crank where I turn this and turn the light bulb on. But what I want you guys to see is what happens inside this magnet. You see right here. Hopefully you guys can see right here. There's a solenoid. So the solenoid is actually part of this generator. All right. There's another example. Another example here of a motor. And actually you can see the north-south. If I had these, keeps wanting to go to the side it wants. But you'll notice that there's a little solenoid here and this little solenoid here. So this is a critical part within our motor or generator. That's the solenoid. All right, I want to show you guys an actual example or a real live example of what she talked about in the solenoid. Oops. So I'm going to go switch to that. Let me go grab that from here. And it's this one right here. And go back and grab it to here. All right, hopefully you guys are still seeing this.
California homeowners.
All right, oh, sorry. Sorry about that.
You can qualify to erase your
I had it ready, but then I lost it. Okay, hopefully you guys can still see this. So this is an actual solenoid, and that's just a piece of metal, zoomed in. And what he's going to do is connect. All right, you can see here. On one side, you see the hole? So they took that cylinder and they just wrapped really tightly the copper wire. It's just copper wire. But he's actually going to connect it. He's going to put that just to show you the piece of metal, a bar. Now he's going to make a connection and add some power to, we don't see the battery here. All right, so no big deal. It's just connected to a light bulb. Now the part you can't see, he's actually going to connect the one side and then the other side actually comes back and he's charging it. He's actually putting some electricity or current through that, and now it's become a magnet. So he puts this, and it did two different things. It attracted that piece of metal before it didn't. And because of that electricity now, because of that the magnetic field, it now also can light the light bulb. Okay, so there's an example of using just a coil of wire in the shape of a solenoid, several loops, to be able to generate some electricity. Okay, let's stop that. The next thing I want to show you guys is how yours truly actually used this on her job. Let me see if I can find this. Where is it? Is it right here? No, it's right here. Okay, so I want to make sure, let me see if I can get guys to make sure you guys are okay here. Where's the chat? Uh-oh, can't see my screen? All right, you guys, can someone text me, make sure you guys can see my screen okay? I'm going to share the screen to this presentation. Okay, let's make sure you guys can see this. All right. I need your right hand a little bit. All right, so I want to make sure you guys can see this, but I want to see, make sure you guys can see this. Have you told me? Can somebody tell me, can I see that? It says radar technology, distinguishing between bikes and cars. Okay, good, you can see it. Thank you, Juan. All right, so I want to give you guys an application for these loops. And whether you're driving or not, maybe you've been in the front seat, you may have noticed that maybe you sat at a signalized intersection, a traffic light, and it stays red until somebody comes up to the intersection. So let's say the main street is always green. Always green. It never gives a green light to the little side street unless there's a car there. How does it do that? It does that by inductive loop detectors. So I'm going to give you guys an example, and then I'll tell you guys what my research here was about. This was my last project. So somewhere on the pavement near an intersection, you might have seen something embedded in the pavement right by the stop bar. What's a stop bar? Stop bar is when you stop to the closest at an intersection. It's a line. We call it a stop line or stop bar. And so it might be this shape, or it might be round, or it might be just rectangular. Let me see if I have the plans here of some. Oh, I must have passed it. All right. So what we use at traffic signals to detect if there's a car there is a loop detector. And all it does is tells the computer, which is somewhere nearby in the intersection, if there's a car there, then, oh, we need to give a yellow to the main street and then a red so that we can finally serve the side street. So now I remember what else I was going to show you. So what the problem was, still is in many locations, is that the loop detectors do detect cars beautifully, but California passed a law that it needed to detect bicycles, because in California, a bicycle legally can drive in the lane. It can go in the left turn lane. It can go, you're supposed to be in the far right lane. The problem though was that the type A, the ones that are just round or sort of like an octagon, it looks like on a square, could not distinguish bikes. So there was a modification into something called a type D loop that can detect bikes. It can detect bikes, but the problem is that it can't tell the difference between the bike or the car. So I did research on a radar detector that can tell the difference between a bike and the car. And then you only have to give the extra green time for a bicycle. Why? Well, they did research. By the way, that's me here, if you can see that. And see, this thing's in the way here, right here in the bottom corner, because it takes a while for the bicycle to go, oh, it's green. Oh, okay, now I need to get up and start pushing. So that takes a lot longer than a car. A car can get through right away. This is the computer cabinet that's somewhere near the intersection with the door open. And I'm going to show you what the controller looks like. Here it is, zoomed in. So in these controller cabinets, you have these, it's called a 2070 controller. And this controller has the detective cards, and there's one for each lane. So each lane has those loops connected to it, and then the information comes to the computer and says, hey, we got someone on the side street. You need to give them, you need to serve them. All right, anyway, I was gonna show you guys this. One of my last projects that I did. Here's a zoomed in on the back side of the controller, and there's a little computer. So these cabinets are usually silver in color. Downtown, I've seen that they've actually started decorating them, but they're usually silver, maybe a greenish color. And that's what's holding the intelligence to be able to detect your cars. All right, so, oh, this was when I finally had a whole bunch of cyclists come out so we could test that location in Huntington Beach. Because the Huntington Beach people, the bicyclists, were just used to blowing off a red light because they would never be detected. And legally, they don't have to come over and press the pedestrian button. They can go straight through. Okay, so let's see. In this case here, you can see the ocean. We're at Huntington Beach, and I videotaped a recorded video, and then the signals when the radar said that sure enough there was a bike there coming. Okay, so that was one example. I just wanted to give you guys an example of what is in your life right now using these inductive loops to detect a car. There's something else I was going to show you, but I didn't bring it up. So I'm going to see if I can bring it up here. All right, hold on. Here we go. Inductive loop detector. See if it'll bring it up for me, because I meant to have it ready, but I don't have it ready for you guys. All right, that's just the actual equipment in there. Not what I wanted. Okay, so let's see. I want to show you guys what happens when I have two wires next to each other. Okay, let me go get this video here. All right, get this one right here. There we go. Okay, copy. Now if I can get Danny? All right, let's see.
My name is John Chase.
Sorry, I have this ready. Okay, so all right. So what I want to show you guys is what happens when we have two wires next to each other. So I'm just going to show you here. Remember? Okay, good. Thank you. All right. So let me make sure you guys have not yet. So here's my right hand, and I have an example of current going up. So you guys can see my thumb is coming up. And
oh yes, going up. Beautiful nails, Ms. Styer.
okay, so you can see that my fingers are going in this direction, so that's counterclockwise. All right, so here's the question. What if I have two wires next to each other and the current is going up? So let's see. I'm going to ask my husband here, and you can see his thumb. All right, so here's what I want you guys to notice. Bring it up here. This hand is going counterclockwise, and this hand is going counterclockwise. But if I put the wires close to each other, notice, no, close, stay there. You notice that mine is going here this direction. Okay, so it's kind of going up, let's say, and he's going kind of down. And what do we know about magnets? Opposites attract. So what's going to happen is that's right, they're going to attract. They're going to want to be close to each other. Now, that's if they're both going up. Now, what if I have one going down and the other one's going up? Notice what happens. Again, his is still counterclockwise. The magnetic field is going counterclockwise, but in mine, I'm going clockwise. So now what happens when I put them close together? This one's going down, his is going down. Therefore, they're both doing the same, then they're going to repel. Okay, they're going to repel. Muchas gracias. Thank you. Okay, so now I'm going to show you guys out with a short little video clip. Share screen. I have it ready here, hopefully. And it's just the first few 15 seconds. Make it big for you guys. You guys can see. Here we go.
It was the autumn of 1820. Hans
Christian Ørsted had just discovered the connection between electricity and magnetism. Meanwhile, a French physicist named André-Marie Ampère was experimenting with some wires, trying to learn more about the connection between currents and the magnetic fields they create. He took two parallel wires and ran a current through both of them in the same direction, and the wires attracted each other. And when he ran a current through both wires in the opposite directions, the wires repelled each other. Studying the strange force between the wires led Ampère to discover one of the most fundamental laws of electromagnetism, what we now call Ampere's law. And that's not the only weird thing that current-carrying wires do. If you wrap a current-carrying wire into a coil, the inside of the coil acts like a magnet. There's a north pole at one end of the coil and a south pole at the other. And if you put a loop of current-carrying wire in a magnetic field, it'll turn. Ampere's law lets you calculate the strength of the currents and magnetic fields in all these situations. This also helps to explain how motors work.
All right, so I recommend that one. So there's two different things that we got to see there. Let me go back to my two different things we got to see there. One was an example of what happens when I have the two right hands. That's why I needed somebody else's right hand. And you saw what happens when the currents were both going in the same direction or if they're going in the opposite direction. There's an actual force. So you remember Newton's was the units for force? There's an actual force that either compels them to come together or repels them and pushes them apart. The second thing was when she showed just one loop being pushed into a solenoid. There was a solenoid and there's a force. And that one uses the left-hand rule. So I think I'm pretty sure that in Google Classroom I put in the links to short little videos that explain that, and that's going to be really critical for your paper. So instead of your final exam, you're going to be writing a paper on how the motor works. So hopefully I'll bring up that rubric for that one. Okay, so the last thing I want to show you guys is this part right here. Copy. Okay. All right, so this is what I wanted to show you guys. I thought I had it ready, but I didn't. So you'll notice these are, this is your roadway, your intersection. They have them along the freeways as well because they want to know how fast people are going. That's another story. And by the way, this was my last responsibility at Caltrans, probably the last, I don't know, 12 years or so. I was responsible for 5,000 signalized intersections. So I don't want to say 5,000 traffic lights because each intersection can have anywhere from 10 to 12 different traffic signal heads, right? Because you have more than one in each direction of the intersection. So the question you can see here is there's a loop. And some will be 3 turns, some are 4 turns. And all it does, the cabinet is somewhere nearby, all it's doing is running some current. It runs some current around that loop. That's all it's doing, is running some current. But we know that because of that, there's going to be there's going to be a magnetic field. And now you guys saw the direction and depending on which direction the current is flowing, then you'll know that there's a perpendicular to it, a magnetic field all the way around it. So on this first picture in the upper left-hand corner, a car starts to drive over, and they kind of move the loops around so you can see if there's more than one loop, but they're really right on top of each other. And so what happens? The car that's metal comes into that magnetic field. Well, when it does that, there's something called a change in inductance because of the change in magnetic field. And that is what your little computer cards that I showed you pictures of is inside in the cabinet, and goes, oh, there's a car, or there's something of metal, because motorcycles do get detected. Their best place, by the way, in case you ride a motorcycle, is over on the edges, because they are kind of sort of either like in a square shape. Here, you can look at over here. In this picture here in the lower right-hand corner, you'll see 3 different ones on 3 different lanes. So maybe this one's going to be a left turn lane, or maybe there's another one's a left turn lane. So this is what I want to show you guys, is an application for just a little solenoid, running current through it, creating a magnetic field so that you can detect a car. Okay, so I'll post this outline in case you're interested in looking at my presentation, because the type D loops, these are all type A loops, by the way. That's a type A loop. The type D loops are the one that can also detect bicycles, but it can't tell the difference between a bike and a car. So the green time was really long. Okay, So at this point, I want to know how we're doing, and I'm going to see if you guys have any questions. So we'll go around the room here. Let's see here. Do I have any questions from anyone?
Miss Styer,
Yes, go ahead.
so after we finish the final and that's it for class, like there's no more?
That's right. And not only is there no more, but I think we're last. I think science is the last final. So you're like no more a senior. You're going to be a graduate, a high school graduate. Yes, that's true. Okay, so the last thing I want to bring up, I want to make sure I get to do this, you guys, is bring up the, hold on, conceptual physics, bring up the rubric, but I can't seem to find the last one that I did for you guys. Maybe it's called research rubric. Let's see if it's this one. Okay, I found it. All right, so let me do a share screen, new share. Oh, you guys can see it. Okay, here we go. So this one I want to make sure you guys understand. Here you go. And I already posted this, by the way. So I do encourage you guys to get started on this now. It'll help you. Your homework should help because it's going to be explaining these. So anyway, let me break it down for you. So out of 100 points for this final, 10 points is organization, and I break it down for what's best organization, below adequate, and inadequate. Your writing mechanics. So I really encourage you guys to use your spell check. I just finished grading a bunch of honors lab reports, and I'm just amazed how many people don't use spell check. I prefer Microsoft Word than Google Docs, but Google Docs must have spell check somehow. So use it, take it, have it help you. All right, so here we go. A full 60 points out of 100 is the contents and the technical explanation. Okay, and yes, bibliography, cite all your sources. Okay, so here's the big deals I want you guys to know and make it that you include. What is an electromagnetic field? So you're gonna have to explain what is an electromagnetic field, and hopefully this, the book and your conceptual physics handouts for the chapter will help you with that, because you wanna explain what I'm trying to start explaining you guys with the magnet, what that is. And then the force, remember that bar that got yanked, pulled into that solenoid, that's a force. And from the force, that's what's making something turn and turn and turn. Okay, and magnetic induction. What does that mean, magnetic induction? So I want it between 7 to 8 pages, okay? And yes, it's a good idea to include some graphics to make your point. Now, if you found that you already explained it perfectly and you want to write a little more, you can add a little section if you'd like of the difference between, and similarities, because they're just kind of one's backwards of the other one, between motors and generators. Okay, so that was the last thing I want to show you guys. Okay, so now let me go around the room and see if I have any questions. We'll start with Jesus. You got any questions on anything, Jesus?
No.
Okay, all right, thank you. Let's see, Juan?
No, all good.
Okay, good. What about Felipe?
All good, Miss Styer.
All right, good, thanks. Let's see, Edgar?
No, I'm fine, Miss Styer.
Okay, great. Let's see, Lupe?
I'm good.
All right, so if you guys have any questions when you start looking into this, you can always email me, of course. Danny, any questions, comments, stock tips?
No, I just think you're awesome.
You guys are awesome. Really, I'm talking about awesome. I can't stress enough how I'm really proud of you guys, because some of you guys already heard this who came in a little early today. The public schools took a really long time, over a month, maybe 2 months, because a friend of mine is a high school teacher at a public school, to even start distance learning. And it's a big disadvantage because, as you guys know, most of the colleges in the fall are going to be exclusively online. Now, the big difference between the online and us, our distance learning, I'd say what you guys have been doing with us might be a little harder because we only meet once a week. Whereas for them, they meet typically around 3 times a week. And yes, I know that if you miss a lecture, they're usually recorded and you can watch it. And I know that there's some sort of, my husband told me this when he was a dean, that you have to respond. Besides homework, you have to show, oh yeah, I read this, here's my comments, that kind of thing. The bottom line is, what you guys have been doing really requires discipline, maturity and discipline. So my hat's off to you guys, because this is it's a lot easier to come into the classroom. It is, you know, and we have the social part about it, and then you can get help, you know, at lunchtime for a class where you turn in, and you don't have that with the online stuff. Now, there have been some of you who've met with me privately on what we call a Zoom. We just did just the two of us a Zoom whenever problems. Of course, I'm happy to help with that whenever you want. But you're gonna have to get more creative on getting extra help if you need it. Okay, so I really want to tell you guys, I'm really proud of you guys because most of you guys have been doing really awesome. So with this paper, since it's 100 points, and by the way, this paper is 25% of your final grade. That's a lot. So for most of you, that can bring you up a whole letter grade. Okay, so really take this opportunity and make the most of it. Hopefully it's fun because you use motors every day in your life, whether you do any laundry, the washer and the dryer, those are motors to make the thing go around. Obviously your car, I'm sure you could come up with a lot more examples, you know, the fan inside your laptop, etc. So anyway, okay, let's see who else. Danny, do you have any comments or questions?
No comments. You're awesome, Styer.
All right, thank you. Yair, thank you so much for saving my bacon earlier today. So Yair, you have any questions or comments?
All good, Ms. Styer.
All right, good, thank you. Let's see, and Helen, if you're still with us, any questions?
No, thank you.
Okay, good. And I think I got everybody who called in. So that's all I had for you guys. I did want to, in fact, if we have time, I'll go ahead and get started on that. The one thing I did want you guys to really make sure you see, and I know that this is going to be a little too advanced for you, but it is the whole point. Let me see if I can go to here, find you guys. Because I have watched this thing more than once, and I really recommend it. I think it's this one right here. All right, so we're going to stop with the left hand rule. So let's stop. Before I get started on this, let me show you guys a picture of the left hand rule. Oops, caramba. Let's go to Google. All right, left hand rule. See if I can get a good picture of it. Okay. Oh yeah, and by the way, this is on my, I should have just gotten the worksheet that I made for you guys. Let's see, do I have it ready? Yeah, here we go. And here, yeah, it's okay. So let me see if you guys can see this. New share. Oh, you already have it. All right, so this is the worksheet that I made for you guys on chapter 20. Okay, I'm gonna close that up. Here it is. Let's see if I can make it bigger. Okay, and make it, there we go. All right, so here we go. I'm gonna come down here to the left-hand rule. So on the lower right-hand corner is called the Fleming's left-hand rule for motors. So you hold up your left hand. Where before in the right hand, we just had the direction of the magnetic field that was kind of going around and the direction of the current. Now at the left turn, we have a left-hand rule. We have three different parameters. We got direction of current, and that's this finger, your middle finger. We have direction of your magnetic field, direction of magnetic field at that point. So that's your pointer finger and the current. Okay, so this hand up here is going to be your current. Okay, so this is important, and I'll show you part of the video, but I'm going to show you guys this right here. This is all helping you guys for your paper. I really want to make sure you guys understand. He does a really good job explaining here. Here you have a north pole of a magnet and a south pole of a magnet. But in the middle, we're going to stick in this little loop. You guys see that, just that little loop. And on one side of that loop, the current's going to go in one direction. It goes around. It's coming out in the other direction. Okay, so in this one here on the left side, we've got, oh, let me see. I think I got that the other way around. You guys can see the little blue arrow. On the right side, it's going out. The current's going out. And then it's coming in. That makes sense, to the negative side. So because the current's going in this direction, where the magnetic field is with the North Pole here, there's going to be a force that's going to want to push that side of the ring up. And likewise on this side, it's going to want to push this side of the ring down. Okay? But then it stops. So we want it to keep going, so we have to reverse the order of the current. Okay, so that's the basic principles. All right, let's see. On this one, here's another way to look at it. Here I have just the magnet, and then the loop's kind of vertical above it. And it's going to want to go away from the magnet. All right, so if you guys are okay, I will show part of that video. I don't know how good it'll work, but we'll try it. Okay, I lost it, huh? Oh, here it is. Okay, let's see if I can make this big.
This rectangular loop is a current carrying wire inside a magnetic field.
Oh, shoot.
That means each side will experience a force. And as a result, this coil might start.
All right, we should get a different version because that one has like Russian translation.
Like in your washing machines, your drilling machines, or even your electric cars. But the big question is, how does an electric current, which is basically moving electrons, push something as big as a fan and make it spin? The secret to these motors are magnets. In a previous video, we had seen that a current carrying wire can be pushed by magnets, or more technically, magnetic fields. So an electric motor uses this magnetic push to spin a current carrying conductor. So in this video, let's explore exactly.
Okay, I'm going to stop right here. So I'm going to make sure you guys have this link. I'll make sure I send you guys that link because it bugs me with the German translation in the middle. All right, so we're going to go back to my outline for you guys because I think we're done. That's what I wanted to show you guys. So unless you guys have any other questions for me, then I think we're good here. We'll end at this point. So if anybody has any questions, let me know. Otherwise, you guys continue doing your good hard work and we'll see you next week. All right?
Bye, Mr. Styer.
All right, take care, you guys. Bye-bye.
Bye, Mr. Styer.
Bye-bye, take care.